Last time we finished the proof of an exponential lower bound fault determinant for multilinear depth 3 circuit. Right, so we showed that determinant or permanent n cross n requires 2 raised to square root n size. Okay, and this is field independent, so this works for any field. And we also noted that we actually don't have such a representation. We don't really know 2 raised to square root n sized multilinear depth 3 representation, but it's quite close to 2 raised to n, so we call it exponential. Now we will try to generalize these techniques, which basically means that we want to continue working with this measure and the matrix, where the matrix is we first partition the variables x into y and z, and then look at the y monomials versus the z monomials, and consider the rank of that matrix. So this generalization was done by Ranraz and Amir Yehudev. So they generalized the prior ideas to get a result for multilinear depth 3 circuit. Multilinear depth delta, depth 3 we have done, but they generalized Raz's original ideas to constant depth, so delta will be some absolute constant. So as delta grows, what will happen is the machinery will become or the parameters will become worse. So we will, instead of 2 raised to square root n, we will get something like 2 raised to n raised to 1 over delta. But this is still exponential for constant delta. So think of delta constant. So fixed meaning independent of s. It's an absolute constant. And in this line of work, the methods also work for formulas. So that will need a slight modification in the measure, which we will see in the end. So let us continue with constant depth. So now instead of a product of linear polynomials, we will work with slightly more general products. So we will call this T product. So a multilinear polynomial f, which is a product of T polynomials G1 to Gt, we will call it a T product. If so there are T polynomials, T factors, and these GIs should depend on at least T variables. GI depends on at least t variables, and it's important that this is multilinear, so these variables are disjoint as you change I. So G1 to GT are basically partitioning the variable set X, and each of these parts is at least t, and there are t factors. So in particular n should be bigger than, should be at least t square. So when we talk about a t product, then we cannot say anything more than square root n product. So we'll need to study slightly general products, because when you go from depth 3 to, let's say, depth 4, so already in depth 4 you can see that you have a sum of products of general polynomials, right? So you have to study the measure on that. So one common generalization seems to be t product, and this will then continue, this will allow you to go to depth 5, depth 6 and so on up to constant depth. But then the results, the parameters will be worse. So let us see that. Let us see the upper bound basically. Well, but before we see the upper bound, we have to prove a structural result about constant depth circuits. So what is the connection between depth delta circuit to this t product, right? So we have to make this connection. So this is a structural lemma. Let f be a multilinear n variate d degree polynomial that has a size S multilinear product depth delta formula phi. So we are saying many things. Most important thing is that we start with a formula phi. Now since we are talking about constant depth circuits, we can as well make them formula. Right? Constant depth circuits are a special case of formulas. So instead of circuit we will talk about formulas, and instead of depth we will talk about product depth. So we are assuming that the addition, so the circuit is actually divided into layers, and the layers addition multiplication alternate. So all these things we can do in the pre-processing. This does not cost much. So we are given this layered formula. The number of multiplication layers is at most delta, so we are calling that product depth. And there is this major restriction, which is every gate computes a multilinear polynomial. Okay, so this is our phi. All of this we can achieve in pre-processing. Then f can be written as a sum of less than equal to s multilinear t products. Where t is something like n to the 1 by delta. Okay, we'll use constants to make the comparisons work, but this is essentially n raised to 1 over delta. So this may come as a surprise. So we start with a depth delta formula, but we are able to squash it into just a sum of t products. So as a sum of t products, and there might be some error part which is a multilinear polynomial of low degree. So degree less than equal to n over 100. So f can be written as a sum of these things, at most s many t products plus some low degree polynomial. Okay, so this is a structural result. This has nothing to do with our measure or lower bounds. Is the statement clear? So once we have this structural result, then we'll convert phi into this sum of t products, and we'll study the measure on a t product and get an upper bound. And we'll see that the upper bound will be smaller than the lower bound on determinant of the measure. So that comparison will finish the exponential lower bound proof for constant depth multilinear formulas or circuits.
This T is same as this T, as f is defined G1 to G2. That is also T, and it also depends on at least T variables.
This is the definition of T product. We'll apply it in the structural statement on some f and on some t.
So I am saying should it be G1 to GT or G1 to GL?
No, it says here multilinear T products. So you have to invoke the definition of what is a T product. Any other question?
Is the error term very big?
Oh, the error term is, no, it will not be very big. It's degree is
It's pretty big compared to what you expect each of your summations to be, right? In terms of the degree. You expect your summations to be roughly degree n by 10,000 to the 1 by delta.
so number of monomials is something like n to the n by 100, right?
If you assume that each of your, in your T product, each of your linear terms actually has T variables or order T variables, then the degree of each of the S summations will be something like T squared, right?
Mm-hmm.
And that's like smaller than the error term.
Well, we'll see. I promise you that in the end everything will be fine. So that is because, so this the measure on this error term will give you something like 2 raised to n by 10 contribution, and we will show that on this T product, well, the contributions will be kind of comparable. So you think of 2 raised to n by 10 as the final measure upper bound, and the lower bound will be much higher on determinant. In fact, I think this 2 raised to n by 10 which we will get for the error term, this will be much smaller than what we can prove for the T products. So this contribution will not matter at all,
We want to,
because we are working against 2 raised to n by 2.
I mean, ideally the objective is to upper bound the measure, right?
Correct. So 2 raised to n by 2 is much smaller than 2 raised to n by 2.
So you would like the error term to have the highest measure, right? So that's sort of how, in general, if you want to lower bound.
No, the error term means that it doesn't matter. This is something which should be dropped, because the measure upper bound for T products will be even bigger. So we'll just focus on them. That will demand the most time. in the proof details. Okay, so this will be proved as always by induction. Okay, we'll just induct on the depth of the formula. Well, note that for product depth 1, when delta was 1, we already did this. The language now may be different, but this multilinear depth 3 circuit, the product depth was 1, and there we were studying product of linear polynomials, and that is what we will now try to generalize to higher depths. So the higher depth case we'll do inductively. Yeah, you are asking?
No, I was saying that we did it for sigma pi case, right?
Sigma, yeah, so we did it for sigma pi sigma.
Isn't it that would be the base case?
That is the base case. So, so you have to see a product of linear polynomials as a T product. Yeah, so you can do it by clustering the linear polynomials actually. So each of your linear polynomials depends on at least 2 variables, we are assuming that. So you can collect T by 2 linear polynomials, multiply them, call that G1, and the next cluster G2 and so on. So by clustering you can actually see that in the base case we did have a T product, and we studied the measure on that. That was, so base case is done, and now we'll generalize it to higher, to more product layers. So let's do that. Right, so if the degree is n by 100 or less, well then everything is subsumed in the error part. Okay, so we'll assume that that the degree of the resulting polynomial f is more than n by 100. Okay, so now since the degree at the root of the formula is more than n by 100 and the number of product layers is only delta, what can you say about the degree demand at some product layer? So there has to be a product layer where the degree goes up by this bound raised to 1 over delta, right? So let's use that kind of averaging. This bound raised to 1 over delta. Somewhere this blow up has to happen. If everywhere the blow up is smaller than this, then you can never reach n by 100. So it says kind of averaging but happening in the exponent, because we are talking about multiplicative behavior. So since phi is a formula, since phi has product depth, has less than equal to delta product layers, there has to exist a product gate V where the degree blows up, so which basically boils down to how many inputs are there. So the product gate should have fan in at least, we have to see. I want to say this, but is it fan in or degree? I think this has to be degree of.
Degree you know additively, right? So it doesn't make much sense to talk about a degree. Multiplication rate, the degree goes additively.
It has to be something else. So maybe it is just fan in. Yeah, there is. That is true. Yeah, this even fan in, so it cannot be degree. Even fan in, I am not very confident now. So let us continue and try to correct this. So the point was that there will be this product gate V. We can assume by induction that this product gate has that form. So it is a sum of
The fan it works. If on any path from the root to the leaf there will be at most delta additive gates, multiplicative gates. So the fan in is less than this at every time. Each time, and then the total degree can only be n by 100, less than n by 100. Because at the first layer, if the fan in is k, at the first layer the degree will be k. At the layer after that, you'll have k at most k multiplication gates, each of degree k. So you get k square.
Okay.
And all the way to k by delta. But then you want that to be n by 100.
Okay. But this doesn't need multilinearity.
No, this doesn't use any assumption.
This doesn't use any.
This is why it's a formula.
Just right. Okay. Yeah. So this comes from the formula. No, for a circuit, I think repeated squaring will create a problem.
Yeah, but you know, if you're doing repeated squaring, that automatically gives you a bound on what the relationship between.
No, but Fanon remains 2. So degree is 2 raised to s, but the Fanon for all the multiplication layers is just 2. So you will never get anything interesting for circuit. So formula is actually important and sufficient. So in a formula you can talk about, just look at the tree structure, and yeah, if every multiplicative Fanon is smaller than this n by 100 raised to 1 by delta, then observe that final degree will be smaller than n by 100. That's all.
But even for a circuit, right? Even if you take your repeated squaring,
Yes.
it will still work, right? Because first, suppose you're doing repeated, you're multiplying it k times instead of just Fanon 2. It just works whatever, you just fix a parameter, right? Even when you repeat a square at degree delta.
Or 2 raised to s times raised to 1 by s is 2. Yeah, that is okay.
So it needs nothing.
I see. This is true for any circuit then. Okay. Right, so this n by 100 raised to 1 by delta we have already defined. This is t square in the lemma statement. And so this is the node which will help us recurse or induct. Okay, so we have this multiplication gate which is V with t square inputs at least, and this will feed into a addition gate. So there is this part of the circuit and there is this part of the circuit, and there might be other, in this multiplication layer you have other multiplication gates and addition layer other addition gates. So how do you want to induct? So that trick you have seen before. This V you delete from this graph, and so that is basically setting V to 0, right? So look at that part and look at the V subtree. So those are smaller, strictly smaller formulas. So let us expand that way. So let us expand the formula with respect to V. So that will give you f equal to phi v is output at V. Something will multiply this, plus the plus part will be when you set this V part to 0. So that is kind of dropping the subtree. Right. So what is the multiplier here? The multiplier is essentially this derivative with respect to V. So I'll just write it as f prime with respect to V. Right. So this is the decomposition of your formula with respect to any node V. Right. So you have a kind of a derivative part times whatever was being computed at V, plus set V to 0, set the V part to 0. So on this we can now induct. So what do you know about these two parts? What do you know about phi V times f prime V? So phi V already has t square inputs. So by clustering we can see that it's a T product, because the definition of T product was very weak. It only wanted a product of T things, each depending on more than T variables, at least T variables. So just by the fan-in you have, and also here we will also use the fact that it's a multilinear formula. So these inputs have disjoint support, disjoint variables. So let's write that down. So as phi V dot f prime V is a product of T square polynomials we can group them it as a T product. So this whole part, actually the part of phi V and times the derivative, this part is already a T product just by trivial clustering or appropriate clustering. The other part, phi V equal to 0, we use induction hypothesis that it is a sum of T products and some low degree polynomial. So this is obviously multilinear. And as phi V equal to 0 is of smaller size, we invoke induction hypothesis. So overall, both these things tell us that f is a sum of multilinear T products and a polynomial of degree less than equal to n by 100. Is this clear?
Sure. That stuff is not clear to me. Phi V times f V prime.
Okay.
So phi V is a product of a bunch of polynomials.
Look at the polynomials being fed into V. No, nothing is, no, there is no demand of linearity or anything. We just want to show that phi V is a product of T things each dependent on t variables.
Wait, could you go back to the definition of the
Sure.
product?
Yeah, that is needed. It's a very weak demand. That's all. Just t things and each dependent on t variables. So, if you are feeding in t square polynomials and the multiplication gate is multilinear, then you can just cluster things and you get this.
These t polynomials require G1 to G2.
Sorry? Yeah, this is in the definition.
All the GIs have to be multilinear.
Yeah, they are not multilinear, then F won't be multilinear.
Then f won't be. Yeah, that is implied.
Stuff could cancel, right?
No. It's just a product. No. So G1 as a polynomial, G1 just sum of monomials, right? Every monomial has to be a multilinear monomial. Otherwise, this monomial you cannot cancel. In a product, how can you cancel a non-multilinear monomial? It will survive.
Also, they are disjoint, so it really doesn't matter. So
Yeah, that also is implied. So if this product is multilinear,
no, if they are not disjoint, then how they can be multilinear?
so everything is implied by the multilinearity of f. Yeah. So just saying this is enough. Right. So those are actually small exercises. I will not prove it, but it can be. You can take it as an exercise. Because we are talking about product, so product is easy to study.
Where did we use the restriction of formulas? Like the first argument was hold it for.
Oh, formula. Yeah. So that is a.
You can do that expansion.
Yeah. So that is a good question. This guy needs a formula. Yeah, so formula is needed here to do this decomposition. This we had seen also when we did Brent's depth reduction for formulas versus circuit depth reduction. That this is Brent's the expansion used in Brent's proof as well. Any other question? Yeah, so this turns out to be quite simple. And we so yeah, did not write here the base case, but I guess you have to be convinced that when product depth is just 1, that is the depth 3. So there you are basically multiplying these linear polynomials, and there also you will cluster them so that it looks like a T product. So this completes the structural lemma. Okay, so now what we will do is just study this product using the measure, the behavior of the measure on a product, T product. So now we need to study the effect of random partitioning. So this is something even more basic. What happens when we randomly partition the variables on a T product? So let f on variable set x be n variate polynomial and computable by size s multilinear depth delta formula. Then you partition equally, size of x is n, and randomly. So when you do this, then the measure gamma yz on f so I'm not just studying product, I'm studying the whole model, but because of the previous lemma, the whole model is just I mean it essentially is a sum of T products, S many. So ultimately the proof will boil down to only studying T product, and what we will say, what we'll get in the end is that measure on F is essentially 2 raised to n by 2 times so S is for the size, so ignore S because so look at the thing we are saying about a T product. So we are saying that its measure is significantly smaller than 2 raised to n by 2, where smaller means that in the exponent we are subtracting by n to the 1 over delta. Right, if you compare this with depth 3, what we had shown in depth 3, there we had gotten n over 48 or something, right. So that was a special case of this. In fact, it was it was, the parameters were very good. Here the parameters are going to the exponent of n even. Right, so the n will actually become, when you take delta to be 2, it will become smaller than square root n. So, so the difference has become smaller now. I mean, as delta increases, difference becomes smaller, but still it is quite significant. Okay, it is n to the some constant. So you are actually talking about 2 raised to n raised to some constant, and that will become your lower bound on S. So it is much bigger than polynomial, it's a nearly exponential lower bound for determinant in the end. Okay, and what is the probability? So this will happen with probability because we have chosen y randomly, with probability significantly high. So the error probability is, if you assume that S is small, then the error probability is small. So this is clearly helpful in the eventual lower bound. So is the statement clear? So we are saying that if your formula has size smaller, where smaller means 2 raised to n raised to 1 by delta, if it has size smaller than this, then with positive probability, in fact constant probability, the measure will be significantly smaller than 2 raised to n by 2. Right, and 2 raised to n by 2 is the max measure possible. So that's the statement. As you pick the partition in a random way, equipartition. Okay, so let's do the proof. So by the structural lemma, write f as G0 plus Gi I equal to 1 to S, where G0 has low degree and G1 to GS are multilinear T products. Right, this we get from the structural lemma. So what is G0's sparsity? How many monomials are there? So we can take a shortcut because we know that G0 is multilinear, right? So if there are I variables, then the number of monomials can only be n choose I. So using that shortcut, we will get a better bound. So n choose I going from 1 to or 0 to n by 100, right? And
Any monomial that involves like d square variables or something, we can just add it in the GIs, right? Okay, then the number of GIs will increase. So yeah, if you want the S many.
yeah, this will come out to be quite large compared to S. So this G0 has to be necessarily separated, and then the number of monomials it has is sigma n choose I. If you are, I mean, this is essentially dominated by n choose n by 100, right, which is something like 2 raised to n by 100. So it is in the right direction, but we can even do this exactly. So this will come out to be by Stirling's approximation 2 raised to H2 1 by 100. So the entropy function times n minus this. So it is 2 raised to entropy of 1 by 100 times n with this small error function of pico of log n will be okay. Yeah, this error is a function that is not more than log n up to a constant multiple. So this cannot change the mean term by much. So assuming n to be sufficiently large, this we can assume is smaller than 2 raised to n by 10. Is this fair? So by Stirling's approximation, we get that G0 has at most 2 raised to n by 10 monomials. What is the measure on a monomial? 1. So the measure of G0 is at most this much by subadditivity. Okay, so I mean in our scale of things, this 2 raised to n by 10 is completely insignificant because we are dealing with n by 2 minus n raised to 1 over delta. So in that scale of things, this 2 raised to n by 10 is actually not important. Okay, so we'll just, once we have this expression, we forget about it, and let's go to the main thing, which is G1. What is the measure on G1? So next we bound measure of G1 for a random partition. So what? So let's replace G1 by G in our subsequent calculations. So let G be this product H1 dot dot HT. It's a T product, right? So you have T factors and each factor depends on at least T variables. Let's say Xi is the variable set. So the variable set of G is X, and if you look at the factors, their variable sets are Xi's. Each of them is at least T, and you have T factors. Right. So what is the action of gamma on this? So when you partition X, it will induce a partition on Xi. So let's call that Yi Zi. And so recall the intuition that if all the variables in H1 go to Y, what is the measure contribution of H1? Just one, right? So if all the variables of H1 are on one side, then it contributes nothing, and quantitatively that intuition leads you to the fact that H1 will contribute the most, or it will contribute more if the discrepancy is more between Yi and Zi, right? So we define discrepancy. So let Di be the difference, value of the difference by 2. Let this be the imbalance between Yi, Zi in Hi for all I. And we'll call Xi K imbalanced. Xi is called K imbalanced if the what? Yeah, this part is just combinatorial. I mean, we are just using the graph, somewhat graph properties, and then mostly probability. So we'll call this variable set of Hi K imbalanced if the discrepancy is at least K, and it will be useful to define Bi, which is the sum of Yi and Zi, which is, well, Yi plus Zi by definition is Xi. Yeah, so Di is the discrepancy, Bi is half of the size, and so if you know Di and Bi, then you know the sizes of Yi and Zi. There is this simple formula. Their sum will give you, in particular, size of the bigger part, and the difference will give you size of the smaller part.
So the pressure will be at most 2 times size of smaller part, right? measure.
Yeah, let us write that. Yes. So if you look at the measure now on this product, so that will be the product of measures. Which is now yi zi, and what is the upper bound on this? So that is 2 raised to min of these. Which is in terms of bi di, bi minus di. What is 2 raised to sigma bi? So 2 raised to sigma bi is just x by 2. Right, and then you are just dividing it by the product of 2 raised to di's. Is that clear? So the point of all this is that, and this 2 raised to x by 2 is, think of this as just 2 raised to n by 2, and we are interested in the amount this n by 2 will fall. So that amount we want to get simply from some di. So in the remaining proof, what we want to show is that there is some I such that di is as big as the thing we need in the lemma statement. So it suffices to show one of the xi's imbalanced. That is di large. Right, so this is what we want to show, and how do you show this? So you do it sequentially. You start with x1, and with your probabilistic choice of y and z, compute the probability that x1 is balanced, and then conditioned on this x2 is balanced, conditioned on that x3 is balanced, and so on. Compute this probability and show that it's small. So which will mean that some xi will be imbalanced. So whichever xi is imbalanced, di will be quantitatively large, and it will give you the expression in the lemma statement. Okay, so now it's a scary probabilistic calculation. Yeah, so brush up your probability for this. So we need to estimate, right, and remember that we are treating xi's as fixed, right. So when we do the probability calculations, x1 to xt are fixed, and they are, whenever needed, we can use this lower bound. They are large sets, and the experiment on which the probability is, in that experiment we are picking y to be n by 2 size subset of n, right. So that is the only random choice. Everything else is fixed in the experiment. So we need to estimate the size of yi on choosing a random y. So n by 2 sized subset y of 1 dot dot n. Yes, I don't know why, but this kind of distribution is called hypergeometric distribution. So it is meant to scare you further. This follows hypergeometric distribution. Yeah, so again you are picking n by 2 size subset randomly, and you are interested in the random variable size of y with a fixed set. Size of y intersected with a fixed set. So how many points have you picked essentially from a fixed set? That is your random variable. And so this is for some reason called hypergeometric distribution. And so we want to compute the probability of that number being something like k. What is the probability? Let's take a detour and compute the probability. So for a fixed set A of size small a, yeah, forget about these bounds, we'll need these bounds in the end. So this is essentially saying that set A is of a decent size, it is not too small, it is not too large. So for a decent sized fixed set A, the probability that a random set intersection with A comes out to be k sized, okay, where R is a random n by 2 size subset of 1 to n. So what is this probability? What do you think? Is this probability large or small? Well, or what do we need in our proof? For our lemma statement, what do you want? Do you want an upper bound on this or a lower bound on this? That you can see. According to the strategy, we need an upper bound. We want to show that this is small, because we'll then invoke this many times and we'll show that the probability of x1, x2, all these things being balanced is small, right? So the direction we want is of an upper bound. We'll show that this is at most 1 over root a. Yeah, which again seems to be Berde paradox, but I may be naive. Again there is the square root a appearing. Yeah, so once this claim is stated, the proof is very straightforward. Right, this is just, you can write down the probability exactly. So probability over R of this being k is what? So you have to first decide which k elements, right? So that will be A choose k, because this set A is fixed. So that's your favorable choices. Once you have decided which k, these you have to then forget. So n minus k and sorry. No, it's not same. No, this is this A and k respectively you remove, because set A is fixed and which k is also fixed, and this divided by n choose n by 2. So it is similar, yeah, this A choose k is now introduced.
That time we had this, everything was small, so that parameter.
No, there
I think the better intuitive way of looking at it is once you fix the k elements you want to
Then it is the same, yeah.
fix without replacement, right?
Without a choose k, it's that. But there we didn't have a choose k.
But that's because a choose k was 1. I mean, we had
Was it 1?
three
No.
We had 3 choose something. But k was 3. K was something small. We wanted to pick triples.
Yeah, it was coming out to be 1. I think we are taking a equal to k then. Yeah, that was a equal to k case.
We wanted triples.
That was a equal to k case, and this is just general version. So call this p of k, this probability, because we have to now make sense of this expression. So to make sense of this expression, we'll need to know how does k, a and n compare. So which is why we have those bounds, the boundary condition of a. Yeah, but it is tricky to analyze. So we'll start with a small observation that if you increase k, what happens to pk? So you can see that as you increase k, the probability will increase, and then at some point it will stop increasing, right? So p of k plus 1 will be more than pk if and only if, well, so write this expression twice, once for k, once for k plus 1, cancel out things, and what will remain? E minus k times do you agree? Sure, okay, great. That's what I wanted to hear. Yeah, so this a minus k and k plus 1 comes from a choose k and a choose k plus 1 comparison, and the remaining this n by 2 things come from n minus a choose n by 2 minus k comparison for k and k plus 1. Right, so you get these two fractions and you just have to compare these fractions. So you can simplify this, and yeah, so let me skip the middle step, and ultimately you can deduce that if and only if k is less than a minus 1 by 2. Okay, this will give you exactly this without any loss. So probability expression increases as long as you don't cross, k does not cross half of a.
So it makes sense, right? Because you expect half of the elements of A to be picked by R. If R was picked, each element was picked uniformly at random probability half, as opposed to from this hypergeometric distribution, then it would exactly peak at roughly A by 2.
Okay, so it depends on whether others agree with this or not. Well, guessing now is not allowed. You should have guessed before. It's too late now. So now this is a proof. So that is your maxima, right? So we can now deduce that p of k can never exceed. Maybe I should make it kind of equal, greater than equal to, greater than equal to, less than equal to, and then I'll just pick k to be a minus 1 by 2. That there p of k reaches its maxima. So that gives you a choose a minus 1 by 2 divided by n choose n by 2. Now who will estimate this? Stirling's approximation, right? But it will really use the most precise Stirling approximation, because if you look at the main terms, they will cancel out. But Stirling approximation has this square root terms. Yeah, so those square root terms will come from this a, n minus a and n. So we will get that. This is big O of square root n divided by square root a square root n minus a. Okay. So good Stirling's estimate. So it really boils down to these lower order terms kind of in Stirling's approximation, and yeah, now you use this another boundary condition that A is not too large, because if A becomes n, then this is infinity, but A will never become n, so we have stopped A at 2n by 3. So this will come out to be less than equal to big O of 1 over square root A. Because these two things, this n over n minus a is bounded by a constant. Is that clear? So that's the calculation. Yeah, so that was a detour. Yes, I'll finish it next time. So for now, remember that we want to compute the probability that all x1, x2, all these variable subsets remain balanced, k balanced. So in particular, k balanced xi is what we want to study. So this will denote by event ei. So let ei be the event that discrepancy is less than k, and we want to study the we want to compute the probability that all these events happen. Right, E1 to Et they happen, and as you are choosing y and z randomly. So this probability is a product of probabilities, right? So this is product of E1, then E2 conditioned on E1 dot dot probability of Et conditioned on the previous ones. So next time what we will do is we will basically compute this, right? We'll give an expression for this and hence get an expression for this product and show that it is as small as claimed in the statement. So then somewhere there is imbalance, and just a single imbalance will give you already the fall in the measure. Okay.